Hi, it's Kifin Lobates here, and today's video is commissioned by Valega Chain Analytics, which is a Helsinki-based blockchain company that performs analysis of transactions on the Bitcoin blockchain in order to help with regulatory compliance in the finance industry. And this video is a Blockchain 101 tutorial. It should be about 20 minutes long, and the intended audience is, for example, cybersecurity professionals who understand technology but are not fully conversant with blockchain. So I'm going to start off by looking at the problem that blockchain is trying to solve, and then I will look at some of the technical implementations that are used in order to provide a solution for the problem. So the issue that software engineers often face when first encountering blockchain is that they think to themselves, well, this is just silly. There's an awful lot of complexity and work to do something that I could do very easily just using a conventional database. And databases have been around since the 60s and 70s, so it's a very well established, very well founded technology with most of the bugs and problems ironed out. So again, why go for something that is only 10 years old when you can build on something that is 50 years old? And the answer to that is that blockchain doesn't fundamentally solve a technical problem. It solves a social and psychological problem. It solves a problem to do with trust. So the big problem that Satoshi Nakamoto, the inventor of blockchain, was trying to solve was the double spend problem in a situation where you don't have a central authority. And this boils down to the problem that cash solves. Cash is not centralized. Well, it kind of is, because central banks print it and distribute it. But once you have cash in your wallet, it's decentralized. It can't be tracked. And what you do with it is difficult to determine. So you can use it for anonymous transactions, and you can use it for transactions where the two parties don't fully know each other or know each other at all. So I can have a bunch of cash in my wallet, and I can see an advert in a paper that someone is selling a second-hand lawnmower, and I can go and see them, and we don't even have to exchange names. I can check out the lawnmower, decide I want to buy it, and hand over the cash, and the seller has no record of who I actually am. And in the physical world, this is easy to do because physical objects are unique. If I have a 50 € note in my wallet and I hand it over to the guy with the lawnmower, I no longer have possession of it anymore. But in the digital world, it's incredibly easy to make copies of stuff. So if you're going to have a digital version of cash, then you need a method to ensure that it can't just be copied in the way that you can copy a JPEG on a website by right-clicking on it and selecting Save As. And this turns out to be quite a tricky problem. And people were working on solving it from the mid-80s, late 80s onwards. Now, I'm not saying that Bitcoin is the perfect solution, but the evidence is that it's a pretty good one. It's taken hold. The value of Bitcoin in dollars or euros has risen substantially from the initial non-value that it had when it was first launched. And of course, as a result, the finance industry and the banking industry have started to pay attention rather than deriding it and laughing at it like they did 5 years ago. Once people actually attribute real value to something, people start paying attention. So I've kind of summarized what the problem is, and what the solution is effectively a ledger. So it's just a list of who owns what. And what you want to be able to do with that list is make sure that it represents a single view of the truth, that everybody involved in the system agrees that this person has this much and that person has that much. And secondly, you want the system to allow a transfer of value from one person to another in such a way that it can't be double spent, so that I can't, for example, send a Bitcoin to one person and send the same Bitcoin to another person. That would allow me to effectively spend the same 50 euro note twice. Now, you can do this in the digital payments world, for example, with credit cards or debit cards, although ultimately the central authority will resolve the fact that a double spend has occurred, either by cancelling one of the two transactions or by reimbursing the person who got defrauded by the second transaction and then possibly cancelling the credit card of the person committing the fraud. So just for clarity's sake, the way that you can do a double spend is, let's say I clone my credit card and I make two transactions with the two cards by handing it to two different people who go to two different areas of the world where the network connectivity is not such that there's a real-time update on the credit card company servers that the balance has already been spent. Anyway, that's an aside. So what we want to do with digital cash is to ensure that our list is presented to all people on the network in the same way, so that everybody has the same view as to what the balances at any given point are. And it turns out this is quite a difficult problem. It's not a problem that database experts tend to deal with unless they're on the edges of fault-tolerant systems. For a normal distributed database, and of course our digital cash system has to be distributed because lots of different parties are going to be keeping a copy of the ledger. So in normal distributed database systems, the CAP theory applies. It's a theorem by, I think his name is Eric Brewer, which says that in any distributed database system you can have consistency, you can have availability, and you can have partition tolerance, but you can't have all three at the same time. And I guess it's worth summarizing what these three things are. So consistency is that when you query the database for a value, you get the same value back each time unless there has been an update, in which case you get a fresher value. You're never going to get back an older value. Availability means that when you query the database, you get an answer back. You're not stuck there waiting forever for a result to come in. And partition tolerance says that if the network splits up, for example, because of network connectivity problems, so now you have two networks, when they rejoin, they sync up, so they end up back in a common state, even if they diverged for a certain period of time. And the CAP theorem says that you can have two of those three, but not all three at all times. And that at all times is important because the CAP theory deals with extraordinary situations where, for example, your network has gone down. And you have this separate network going its own merry way. Most of the time in distributed systems, if everything's running smoothly, you don't need to worry about the CAP theorem because you can have consistency, availability, and partition tolerance. But when the network goes down, or when an individual node fails, then the question of partition tolerance or availability kick in. And it's kind of a business decision to decide which is more important to you. For example, if you have a distributed database keeping track of the stock of pairs of socks in various warehouses, you're probably not going to be terribly disturbed if occasionally you get a slightly inaccurate result and you're told that there are 2,000 pairs when actually there's only 1,950. So in that case, a business might choose to go for availability rather than consistency. Whereas if you're dealing with a system that is processing multi-million-dollar transactions, then it's going to be important to have consistency because you don't want to make a financial decision on the understanding that you have 50 million in an account when in fact there's only 20 million there. That could be disastrous. So a further thing in database theory is the question of malicious actors, and this becomes very relevant to Bitcoin because Bitcoin is an open permissionless system. Anybody can spin up a node, anybody can participate in the addition of transactions to the network, and they don't have to identify themselves. So the classical problem in computer science to do with malicious nodes on a computer network is the Byzantine generals problem, and it uses an analogy of a group of generals who are planning to attack Byzantium and overthrow the king, but they know that they all have to coordinate their attack, and some of the generals may secretly actually be loyal to the king. So the problem there is, how do the rebellious generals manage to synchronize their attack in a safe and secure way, so they only commit to their military action if they know that they are going to win? Because if they don't win, they're going to be executed by the king. That's the kind of kicker to this analogy. But the issue with the Byzantine generals problem, which was partially solved before Nakamoto came along, is that you don't just become a general by deciding you want to be one. The parties involved are all identified, and they have authority to order armies around. And this analogy carries over into the solutions of the Byzantine generals problem in computer science, in that, again, you have all these nodes, and although you don't know whether they're malicious or not, at least you know who and where they are. Now, that means that classical solutions to the Byzantine generals problem don't apply for Bitcoin, because we don't know who the nodes are. They haven't applied to join. Anybody can just join. In the same way that, provided you have a means to obtain cash, for example through a job, you now have this cash anonymously. Once it's in your wallet, it can't be tracked by a central authority. So Bitcoin provides a solution to this Byzantine generals problem in a situation where you can't identify all the parties. And now I want to talk a bit about the ledger that Bitcoin provides. So, as I said, it's a list of who owns what, but you don't know who is. They're identified pseudo-anonymously by their Bitcoin addresses, and anybody can create any number of Bitcoin addresses. In fact, it's generally advised that when you are using a Bitcoin wallet, that you create a new address for each transaction, precisely to improve the anonymity of the system. So this is where companies like Valega come in, because although the majority of transactions that take place are legitimate and fine, there is a certain percentage that are against legislation for the prevention of money laundering, or the financing of terrorism, or other nefarious human activities. And it's become a bit of a headache for the financial regulatory services and for the companies that are trying to provide Bitcoin and blockchain services to comply with the regulations that are being applied and tightened up all the time, precisely to try and prevent these kind of activities. So it turns out that Bitcoin is not as anonymous as it might first seem when you look at it. Just because people are hiding behind Bitcoin addresses doesn't mean that we can't infer some things about what is going on in the transaction world. And this is precisely because the blockchain does provide a transparent open ledger of who created Bitcoins and who they transferred them to in terms of their addresses. So we have a network of transactions, a graph, if you will, of transactions, and we can start traversing the graph and see how the amounts are moved around. And as a result, if we can identify a participant on the network as a real living person or corporation, we can start drawing conclusions as to where the likely destinations are, or more easily, what other addresses that same entity controls. And that's exactly what Valega does as its core business. So a bit about the technical implementation of Bitcoin. I've talked about this ledger in the abstract, that it's this list of addresses and balances, and the blockchain has a complete historical record of how that list has changed. Now, there are a few things you need to understand about how transactions work, and that is, if you have a wallet and it has a balance associated with it, then you can send in a transaction to transfer some or all of that balance to a different address. Now, the immediate gut reaction for implementing such a balances ledger would be a simple traditional accounting method, which is to have an address and a balance, and then if there's a transfer out of some of that balance, you decrement the balance associated with the address and you increment some other address by the same amount, and you just make sure that there's a conservation of the total amount in the account. This is traditional accounting has seen for centuries, but Bitcoin doesn't handle transactions in such a way. Instead, it uses the concept of inputs and outputs. So rather than having snapshots in time of absolute values, you have a more dynamic system whereby an address receives inputs. That's kind of like a promissory note that they have some balance to spend, and then they spend those inputs in the form of outputs, which become inputs to the next address. Now, it does sound a bit complicated, and to be honest, it is one of the concepts in Bitcoin that it can be a bit difficult to understand. But I use this analogy that you can imagine inputs as being cups of sand. So the sand represents the amount of Bitcoins or Satoshis, which are the smallest units of Bitcoins that you can have. And then when you spend those inputs, it's like tipping the cup into somebody else's cup. Now your input, your cup of sand, has been emptied and someone else's cup has been filled up. So your input has become an output and they have received a new input. And it's this flow of sand between cups that constitutes the graph that I was talking earlier about, of the flow of transactions through the system. So then we have the second issue, which is you submit a transaction, but it's not immediately added to the blockchain, which is this distributed database of all these inputs and outputs. It sits in something called the mempool, which is a list of all the unprocessed transactions. And miners on the blockchain are then churning away, performing this thing known as proof of work, which is evidence that they have committed resources to maintaining and extending the blockchain network. And they pick up the transactions and package them into blocks. You've probably heard about this already. And the blocks are effectively, through the proof of work system, selected in a sort of lottery manner. The luckiest miner gets their block added, and miners are incentivized to perform this mining activity by receiving the block reward. That's also how Bitcoins are created over time. And the miners also get to take something known as a transaction fee. Every transaction has a small charge levied on it in order for it to be included in a block. That charge can actually technically be zero, but then it's less likely that a miner will pick your transaction and include it in a block, because there's only so many that they can fit in. So they're going to pick the ones that will pay them the most. And this structure of taking transactions, putting them in this sort of unsettled mempool, and then later packaging them into blocks by miners and paying the miners rewards, is one of the things that gives us a lot of information as to what is going on, because the miners are somewhat easier to identify, particularly because they often operate in pools. One individual miner may not have enough resources to have much of a chance at finding a block and receiving a big reward for doing so. But if a lot of miners pool together, then what they can do is they can decrease the payout that they individually get, but increase their chance of getting one. It's a bit like joining a lottery syndicate at work, where you know that your chance of winning the lottery is very low, but if you pair up with 30 other people, your odds increase. However, then you have to share the winnings with everybody else. And these mining pools are more easy to identify, so they give us one route into looking at where transactions are coming from and where the creation of Bitcoins is starting. So that's a first useful thing. The second thing is that unlike traditional financial transactions, which have very clearly defined parameters, the Bitcoin system uses something called a scripting system. So most of the transactions are fairly standard and recognized, but there is the option to build fairly esoteric financial transactions in the Bitcoin system. And it's up to the individual programmer how they decide what order they do things in and what functions or controls are executed during these scripts that perform the financial transactions. And this leaves a fingerprint on some transactions. If you're using one piece of wallet software rather than another, then there can be subtle differences in the way that the transaction is worded, I guess is the way to put it, that give you a hint as to what software they're using. And that is another tool that can be used by an analytics company such as Valega to trace the flow of value through the system from known to unknown and back to known users, which of course is very useful in the tracking of what is going on in the Bitcoin world. And then the final thing that gives us another hook into what is going on in the system are the exchanges. Now, the reason why exchanges exist is because there needs to be an on and off ramp for cryptocurrency to connect it back to the fiat world. And the reason for this is that not many vendors and service providers in the world are willing to accept Bitcoin as payment. Most of them want good old-fashioned dollars or euros for their services or for their goods. So and similarly, people who want to actually have a shot at owning some Bitcoin are probably not going to have the resources to build their own mining system, nor are they going to have the technical skill, so they just want to buy it. And these exchanges are the final piece in tracking down what is going on in the system and actually being able to identify parties who are involved in transactions, because those exchanges are centralized. It's where you move off the decentralized world and into the centralized world, and as a result they are easier to regulate. They can be subpoenaed in order to provide records, and their addresses are often fairly easy to discover. If you sign up to an exchange and you send them some of your cryptocurrency, then the address that it goes to must obviously belong to that exchange, and now you have something for your database that says, this address is owned by this cryptocurrency exchange. And that then allows you to do a whole load of other investigating into what other funds have been going into that exchange, and start tracking further what is going on in the ecosystem. So it seems like I've talked more about the technical stuff and how it's used by chain analytics companies like Valega to shed a bit of light onto what is going on in that world. I hope you found this video interesting, and I'll see you in the next one soon. Bye for now.